Welcome back. So in the second video I want to explain to you how FlowDroid actually obtains high precision. So compared to what I already showed you with synchronized pushdown systems, you have to understand that FlowDroid was developed about 6 years, oh, 7, actually 8 years back, right? That's when we started. And with synchronized pushdown systems we can even reach higher precision right now, but back then this was still way beyond the state of the art. So it was a relatively precise analyzer, and some of the concepts that I already explained you will also see in some first instances already here in FlowDroid. So I've already shown you that there are a number of technical sources of imprecision, but I briefly want to recap these here. So you can have field, context, and object and flow sensitivity, or also insensitivity, right? And some of the Android taint analysis tools that have been published earlier, well, actually all of them were failing in some of this regard, right? So I don't think there was a single one that was field sensitive before, and they were also not context sensitive or object sensitive. I think they were only flow sensitive, and that was about it. And so FlowDroid was really the first tool that sought to combine all of these different properties. And why are they important? Well, for instance, in this case, right, if you're assigning something to AF and you're printing AG, then of course you want to avoid a false positive here. So you would normally get a false warning if you had a field-based representation like you see here, where the field is ignored, right? So, sorry, that's a field-insensitive representation, so we don't really want this, right? Some analysis also use this A star. That's also not helping. As you already have learned in DECA I, we really need field sensitivity, so the field identifier needs to be tracked somehow through what you already now know is called an access path, right? Then the other thing, of course, is context sensitivity, right? So here I'm assigning a private and a public key value, and eventually you will see that the public one is being printed here. But if we don't have a context sensitive analysis, then you know that this will be over approximated, right? So we may have a flow that is actually being propagated from this private value here back to this y variable here, which is then eventually leaked, right? So basically this data flow, and that will then again give us a false warning, which we don't want. And that's of course why context sensitivity is so important. And like I said, again, previous tools, they didn't really implement it that way. Yeah, so what you see here is basically how it needs to be dealt with, right? So we want to have a procedure summary actually for this identity procedure here that tells us that whatever parameter we have s, it's actually mapped to the return value. And then at the first call site, this will apply to the private key, and at the second call site this will apply to pub, the public key, and so these two values can be properly distinguished. But then we also found that in Android you actually also really need some level of object sensitivity, and this again I want to show you here. So let's assume we're having these two different wrapper objects. So W1 is actually wrapping a public key, and W2 is wrapping a private key. So the private one shouldn't be leaked, the other one is fine to leak, and in fact we are leaking here the public key, as you can see. So we're leaking out of W1, which is just defined as this container object down here. And if you don't have an object-sensitive analysis, though, you would get also, again, a false warning here, because then we couldn't distinguish anymore between different fields of different owner objects, right? But if you have an object-sensitive analysis, then this can be distinguished. And what's actually interesting is that if you use an access path based pointer representation, then as we found actually in this work, you get a certain level of object sensitivity already out of the box, simply because these different objects are distinguished by the different access paths that describe them. But here, yeah, in this case, if we were to propagate, w1.value, then you would actually obtain this problem that you see here. So we solved this in FlowDroid in particular, not with synchronized pushdown systems because they hadn't been invented yet. Instead we actually chose bounded access paths. So this means if you hit an access path such as here, where you maybe have some local variable v, and then a pref next, pref next, pref next pointer, and so on. So some, in this case, W-link data structure that, these access paths, they could go on forever. In this case, in FlowDroid, we introduced an artificial constant k that can be used to actually bound these access paths. The default was actually 5, like you can see here, so it was already relatively high, but it's a command line option, so you can actually lower that if you are trying to obtain a more efficient analysis. Although I have to say that lowering the parameter doesn't necessarily always make the analysis more efficient, because as you lower the parameter, you also, of course, get less precision, and then you might get larger over-tainting. So you might be tainting actually many more variables than you would get with longer access paths. And yeah, so there's a certain trade-off involved here. And it's not always clear also in terms of runtime efficiency what the best k value is here. And that's again why also SPDS are so appealing. There you don't need any bounding, and you don't really need to deal with this problem at all, because it's all taken care of you by the pushdown system and its post-star automaton, just by the way it is constructed. Let's take another look at this example here. And this shows why it is important to also have flow sensitivity, because here what you see is actually we are assigning the private key to pry, and then pry is also assigned to x, but only after x has actually already been leaked, right? And so we are not actually leaking the private key. That's why flow sensitivity, of course, matters. Now, what's interesting is there have been a couple of papers on flow insensitive taint analysis. So they are really actually using blown up pointer analysis in the sense of Spark or similar algorithms, so Anderson style pointer analysis, to actually model taint analysis. And one of them has, for instance, been implemented in the Duke framework. And what I found interesting is that among all these different sensitivities that I just described, apparently flow sensitivity is the least important one. So even with a flow insensitive analysis, you can get away pretty much, so you still get rather decent precision, because these kinds of situations apparently don't happen too often in practice, right? But of course they can happen, and if you want to exclude such false positives, then you need flow sensitivity. And that's also why we implemented a flow sensitive analysis in FlowDroid back then. But there's still one interesting challenge, and that is that aliases, they may be created before an actual taint is created. So let's take a look at this example. So here we have two objects x and y, and we alias them, okay? And only after that we actually start with a taint flow analysis, right? So here, this is actually where the analysis will find its source, and this is where it will find its sink, and it will try to detect a data flow between the source and the sink. And now if you do this naively, you could do a demand-driven analysis that simply has this as its entry point. So it simply starts at the source and analyzes moving forward from here. But then if you're not careful, you would miss this aliasing relationship, right? Because the aliasing relationship was already defined up here. And so what this means is you really must look into the past. You must look backward in order to find these aliases. At the very least, if you are doing a demand-driven analysis. And in FlowDroid, we actually wanted to do a demand-driven analysis for efficiency reasons, right? So the other way would be to do a whole program analysis that just always goes through the entire program, starts basically, in this case, at the beginning of the activity, right? And then you would pick up this alias relationship, in any case, but it would also mean that you would need to keep track of a lot of aliases that maybe don't have anything to do with your taint flows and that are irrelevant to you, right? And that's why we decided to do it differently. So in FlowDroid, you will already see sort of a cheap, poor man's version of what we these days have in Boomerang. So basically, we do a demand-driven forward pointer analysis, and then some variant of a backward alias analysis. And that then works as follows. So for instance, we could have a taint flow to some variable A, and that will then be put into the work queue of the taint analysis. And if A is then assigned to a heap variable, like you see here, so x.f, then we are now interested in aliases of this field, right? So basically, we ask the backward analysis what could be other aliases for this field here, right? And you can already see that this is somewhat different from Boomerang. In Boomerang, we would be asking a query only for the base variable, only for x, and the field would be left implicit because the field only matters to the taint analysis, and the task of the alias analysis is really to find aliases of the base object. But in FlowDroid, we still had a design that was sort of mixing both. So we were sort of keeping track of this field also in the backward query. And anyway, so then when the backward analysis would find such an aliasing relationship here, it would then tell, again, the forward taint analysis that y.f might actually also be a potential taint, right? So this is actually not even telling the analysis that this might be an alias, it's even already telling it this might be a potential taint. So in FlowDroid, we didn't really have a clear distinction between the alias analysis and the taint analysis. It was sort of, both really almost the identical analysis implementation, except that the one was going forward and the other one was going backward. And yeah, this is a technical detail. So we basically have a counting thread pool executor. So what this basically means is all this is running concurrently in multiple threads. So we have worker threads running the forward analysis. We have worker threads running the backward analysis. And in the end, when all of their work queues have been depleted, when everything has been processed, then these threads will actually terminate and the analysis has been successfully completed. Now, this is then also how this works, right? So we would basically start from the source here and go forward. Then here we would find a heap access. This is, of course, propagated forward as well. But because it is a heap access, we would then trigger also this backward analysis, searching for aliases of x.f. This would then find an alias z.g.f, which the IFDS solver would map back into this context as an a.g.f. And this would actually be propagated further to here. And now, because we reach an allocation site for a, for the base variable, we know that we can actually stop the backward analysis here. And from this point, it will propagate forward, actually attained for b.f at this case, in this case, right? Because here we have an alias b for a.g, right? So a.g.f is turned into b.f at this statement. Now, what's important, and I'll still be talking about this on the next slides, is that what is being propagated here, it's not really an alias, it's already attained, and this can give us trouble in certain situations. So Let's assume we have such a program here. So here you will see a sync call before the actual call to the source. And here we have a sync call after the source. So here we are actually leaking the data item of the source because P2 and P are aliased here. Okay. But here we don't, right? Because the source hasn't even been called. But if we are not careful here, then the way this analysis was designed, we could actually get a false positive. And why is this? So here the source is being assigned to p.f, right? So p.f is actually being tainted. And now this would trigger a backward search, but within FlowDroid, we're not using boomerang, so this means we are really looking for aliases of p.f. Okay. And now when we reach the allocation side up here, this again triggers a forward analysis, but like I explained to you, this is now a forward taint analysis. It's not an alias analysis because, in boomerang we would be propagating aliases now, but this is within FlowDroid, so we are propagating taints. And the problem is now, we're propagating a taint for p.f, which is being turned into a taint for p2.f here, which gives us a false warning at this program statement, right? So the analysis would assume, although that's definitely not the case, that there can be a data flow from this source down to this sink. So essentially we lose flow sensitivity in certain situations. And that's not good, right? And that's actually something that we wanted to avoid. And we wanted to make sure that these kinds of false warnings don't happen. And so the way we dealt with this in FlowDroid, that was the rather crude solution, was that we took the source statement here as what we called an activation statement. So that basically meant that if we had such taints that, like they come down from here, taints that are created from the alias analysis basically, then at first they would be inactive. So they are being propagated and we track their aliases and so on, but they wouldn't really trigger a taint analysis warning unless they would later on be activated. And activation would happen when, and if and when I should say, this actually passes by the source statement. And so at this point, the taint is not yet activated, so we won't see a warning here. Here it will be activated, and then basically we get a correct warning at the sink down here. So that then gives us the correct warning down there. Now this worked, but by now we know that there can be more elegant solutions, right? So if I were to design this again, we would simply use boomerang under the hood. Then you would have a clear distinction between what is actually a taint and what is an alias. So basically everything involving the backward and forward query would be left to boomerang, and that would be tracking aliases. And then only when we were to come back to a certain statement, such as this one, would we incorporate the aliases and convert them back into a taint, and then the taint analysis would start back here. But essentially it's a relatively similar effect. So in terms of analysis precision, I'm not even sure it would make a difference, probably not even. But in terms of elegance and ease of understanding and so on, this definitely was not the most elegant approach in hindsight. The other drawback is, of course, because we need to have this activation here, the taint itself that we are propagating here, it needs to carry additional state, right? Because we need to know for each taint whether it is active or not. And that means you have a somewhat larger abstract domain. It's not a lot larger, but a bit. And that's, of course, also not nice in terms of summarization and so on. You have learned all of this in DECA I. Now, there's more special care to be taken. We must also make sure that we inject the right context information from one analysis to the other. So that means the backward analysis should only visit the contexts that are relevant to the forward analysis and so on. I've already explained that when I was talking about boomerang and pushdown systems. So we must keep these calling contexts in sync. And yeah, like I also just explained, we need this extra state to control taint activation. And all of these details are also explained in a bit more detail in this PLDI paper. So I encourage you to take a look and find more details there. In the next video, I will then still be presenting to you some experiments that we ran and also some results that we obtained. See you then.